right, class, how are you doing? My name is Mr. Larry Watlington, and I am your instructor for, yes, you got it, NAM 320, Computer and Operating System Architecture. You know, I'm looking forward to this class. I think it's going to be really a fun class. Don't know you guys' backgrounds, but I'm reading through those, but I'm sure that at this point, if you take a 300 level class, you've had some exposure to computers, operating systems, and some of those things. Now, I will tell you, as we go through this series over the next 8 weeks, we're going to have a lot of fun. And the things that I try to bring to you are things that I've gained over my years of experience. So I'm not going to be really regurgitating a lot of things that's already in the class, already in the PowerPoints, but maybe taking some things from a different perspective, hopefully opening up some opportunities and some learning experiences for everybody. All right, so let's take a look at this first week. Week one, we're talking about technology and system architecture, okay? So with that, let's do a quick overview of what this week consists of. Chapter one, is computer technology, things you need to know. And then there's, you got some review questions in chapter one. Now in chapter two, what you're going to be doing in chapter two, which is Introduction to Systems Architectures, you're going to actually have a research project. There's also a PowerPoint slide in there as well. Now with this video, I'm kind of encapsulating chapter one, chapter two together, okay? Now this research project, make it fun, okay? What you're going to do, you're going to go out you got a scenario where you're going to build a computer, right? You're going to build a workstation. Now, whether you go to Newegg, CWD, Tiger Direct, you can go to bestbuy.com, whatever website you want to go to, and you're going to find the components, whether it's going to be memory, RAM, your graphics card, case, power supply, CPU, all the different things you're going to need to build your system. So that's week one, kind of from an overview. All right, let's talk about, and then, I'm sorry, also we have a quiz. That's right, there's your week one quiz. Now, before we get into this class, and the thing I like about this class as I've gone through the material, it focuses on an area that I really enjoy, okay? The architecture. Architecture takes us to the why, and not so much the how. What are you talking about? Yeah, let's look at this. Some food for thought. This is something I learned years ago when I was on active duty in the United States Air Force. I had a commanding officer who told me this once, and I never forgot it as a young airman. He says, people who know why will always tell people who know how what to do. Think about that for a second. Let that marinate for a minute. All right, here's what I'm talking about. You see these guys right here? I don't know how many football fans you have out there. I'm not really a fan, but this makes a great analogy. But football players, NFL, okay, and then this is, I found a picture with one from every team. So no matter what your team is, you're represented. But these guys know how to play football. Yeah, and some of them are very good at that. They have perfected the skill of playing football. You see these guys? These are football NFL owners. They know why you're playing football. And that is why, no matter how often these individuals strike and go on strike, these individuals will always be telling these individuals what to do. And just take a reasonable guess. Where do you think the most money lies? Here or here? Who's getting the bigger piece of chicken? You got it. These guys right here, because they know the why. So what does that mean? That within this course of architecture, not just talking about how to build a computer, but it's the why. It's the why components work together. It's why it has to be put together in the way that it is. It's the system architecture behind that. And what a segue. Now, let's talk about word etymology. And me personally, I love this because words, there's so much power in words. But when you think about this word architecture, what does it mean, right? I'm sure we've all used this word a lot. You've heard it used a lot, architecture. What does that really mean? I think it's pretty interesting now when we start to dissect this word and see where it comes from. Well, the word architect comes from the Latin word architectus, which comes from the Greek word architecticon, right? You're like, really? Are we actually doing word etymology in a network computers operating systems class? Yes, we are. Here's why. Because it goes back to the why. Now, if you take this word, right, the Greek, and you break it apart, it gives you two words. Archi, which means to be the first, or who commands. Tecton is a mason or a builder. So when you put those words back together, architect, that is the person who commands, or the boss, who sends the builder. Okay? It's like, here again, these are the people who know how, these are the people who know why. So when we think about this word architecture, now putting that ending on it, that's the communication plan or design that the boss, or the one who commands, sends to the builder. So when we're talking about architecture, we're here again, we're talking about the design, the communications plans on how components have to come together to build a system, whether it's to build a computer, a single computer, whether it's which was composed of various components, or how you take that computer and other devices and you build a network, and how you take that and you continue to build out to build large infrastructure. But it is the communications plan and design. It's not just the individuals who know how to put components together, but it's how those components were built and how they have to communicate, and the design behind that. Now, yes, you do. You get a Bible study with me every week. All right, this week, when we're talking about architecture, let's talk about biblical architecture. You're like, what? Biblical architecture? Yes. When we think about architecture from a biblical perspective, God often shows us many things. But one of the things that I think throughout, we look at how the Bible was written, how it was canonized, and how it was brought together. It takes us on an architectural flow from data to information to knowledge to wisdom. And what do I mean by that? All right, so if we look at this, if you just take the Bible, right? The book itself, what is it? What is it, right? It is just a collection of symbols. Alphabets, numbers, symbols. That's data. Those symbols by themselves really doesn't have any meaning. It is just a bunch of symbols that is printed on paper. Now, when I take that, and so this will be like the first level of our system architecture. I got data. Now, I read that. I read those symbols. What is that going to give me? That gives me information, right? Very similar. If you go to Acts, the book of Acts, chapter 8, verse 26 to 39, when Philip encountered the eunuch. The eunuch was reading Isaiah. Oh, he was reading it. He took that data and he was ingesting it and he was getting information. However, here again, he didn't have the full design. He didn't have the full communications plan because he needed to take it to a next level. He needed understanding, and that's what Philip brought. So when we look at the next level, which goes up to knowledge. So now, when I take these symbols, I've read them, I've gained information, and now I start to study. That's when knowledge happens, okay? That's when we start getting knowledge. Like the scripture says in Psalms 1, 1 and 2. Delight yourself in the Lord. Okay, delight in the scriptures and meditate. David talks about meditating. Okay, study to show yourself approved. Workmen that need not be ashamed, rightly dividing the word of truth. That's Timothy chapter 2:15. So you see now we're building a design, a system design, an architecture. Now, you see the top of that isn't quite built out yet because that takes us to the last round, which is wisdom. That's the application. Wisdom, yes, the principal thing, get wisdom. But in all you're getting, get an understanding. So we can look at wisdom and understanding. But you see this as an architecture? Not just a canonization of words, but God gave us an architecture. Because he's the boss that sends the communications plan. All right, now how do we apply this to our computing system? All right, so let's look at basic computer architecture. Okay? And this is really any type of information system. It starts with an input. You got to have something, you got to input. Now, with a computer system, we're talking about keyboards, mouse, could be a webcam, though anything that brings an input in. Then that input has to be processed in some manner, some form. And that's where our central processing unit comes in, the CPU. That's where the manipulation of data or the processing of data takes place. And then it just can't sit there because it's pretty useless otherwise. So there has to be some type of output. And that output could be a printer, it could be monitors, it could be a network card where it sends it to somewhere else. But that is the results of the processing of the input. And the last part of that is storage. Because after we have processed that data, typically we want to keep it somewhere. So that's where we use storage. So now this is your basic computer architectural design. So no matter what, if you're talking about a laptop or a desktop computer that you use every day, or if you say, let's talk about an embedded computer like your Roku device at home. That does, yes. It has an embedded computer. It's probably a Linux core that's running in there, but it's doing the same thing. It's taking inputs either from your remote control or from somewhere else. It's processing that, and then it gives an output, which is usually, the picture on your TV that you want to see. And it has storage because it saves all of your configurations and everything. So so it doesn't matter if it's an embedded computer, if it's a standalone computer, your phone, anything that has some type of computational process, it has these 4 basic designs. Now, when we think about this design, there's some basic components you need to be aware of. Excuse me. So we look at any type of computer components, it starts with hardware. Okay, when we're talking hardware, here again, we're talking about your CPU, your motherboard, memory, storage. We're going to talk about those a little bit more in depth. Now, on top of that hardware, this is where we install an operating system. Doesn't matter what that operating system is. It could be a Windows, it could be Mac OS, Linux, depending on your operating system of choice. But that operating system, it integrates directly with the computer hardware. Then on top of the operating system, this is where we install our applications. It could be Word, Excel, PowerPoint, your video games, whatever, Adobe, whatever it may be. So you see we have, again, a design structure, an architecture from hardware, operating system, applications. And then we, as humans, or other computers, that's how we interface. We interface it with I/O, with input-output devices. Pretty basic, right? Yeah, that's kind of the design of a basic computer. Here again, it could be a desktop, it could be a laptop, or it could be an embedded computer system. It could be any of these things that you're still going to have some type, that's a very similar architectural flow with that. So let's peel this back a little bit further. We've been talking about this thing called CPU, your central processing unit, right? So what does that actually do? So and then this is I'm going to base this on a home computer, laptop, desktop. Within that device, you have a motherboard. Now, on that motherboard, you have multiple components, right? You've got your input-output ports, like USB ports. It could be video display ports, whatever it may be. All those are connected, which gives you your input-output. You also have a thing on here called your CPU. This is where your CPU resides, is on this motherboard. Now, what does that CPU actually do? Well, it's really not as smart as we think it is. It's fast, but not as smart as we sometimes think it is. It really does 4 processes. It has a control unit that does decoding. It has a arithmetic logic unit, and then it has memory. And that memory does the fetch and store. So let's talk about this. So when we look at this control unit, the control unit, like I said, what that does, that does the coordination and the control of all your systems, your computer's functions. So, and within this control unit, it manages 4 basic processes. Fetch, decode, execute, and store. All right? So fetch means that you've got something in memory. We got memory, so there's some code in memory. The control unit says, okay, let's go get that code, bring it up, and then that control unit, that's where it's going to decode that, or say, okay, it's going to take those lines of code and read it, says, oh, this is what you want me to do. I got it. And then from there, it's going to send it to the ALU where it actually executes that. And then after it executes it, it puts the finished product or results back into memory. It's kind of like cooking, I want to make something. So what do I want to do? Well, I'm going to go fetch my cookbook. Yes, I go get the cookbook off the shelf. And then I'm going to decode it. I'm going to open up and read it. What am I making? I am making, apple strudel. So I'm going to find the recipe and decode it. All right, I need apples, I need the sugar, brown sugar, cinnamon, all of these different things. I've decoded that because I am the human control unit. Now what am I going to do? I'm going to take it over to the ALU where let's execute. Get these components, get these ingredients, put them together, make that strudel. What do I do when I finish making the strudel? I do two things. I store it. Now I'll take that, put it in the refrigerator, and I also am going to store my cookbook back on the shelf. Pretty much what your CPU does, but it does it really, really fast. And like I say, in this over here, this area where the magic happens, in this ALU, really it is a huge calculator, adding machine. Within this, really all it is really doing is mathematical computations, adding, subtracting, multiplying, dividing, or doing a comparison. And when we think about all these different lines of code, as it executes those, that's really all it's doing, because we're talking about binary ones and zeros code. So it's not doing as much magic as we think. It is just doing simple things really fast. And when we talk about storage, the storage area down here, think about storage really in kind of three aspects, right? You've got registers, and what a register, if you have, is really that's holding the data that the CPU is currently processing. And you have another type of register, and sometimes we call this, cache level 1, level 2, actually level 3 cache. That just helps it do it that much quicker because it's so close to the CPU. Also, other types of memory, like RAM. Now, what RAM does is hold the program instructions. Okay, so you have, you have multiple types of memory. We're going to talk about this memory a little bit more. But you got, your primary memory, which is the RAM. You have secondary memory, which is your hard drive. And like I said, then you have your registers that holds what's actually being done right now that CPU is working on. Kind of goes back to our cooking analogy. My shelf where my cookbook sits, that's secondary storage. I pull it out and I lay it on my kitchen counter. My kitchen counter, that's primary storage. All right, so I got my cookbook laying right here. This is giving me the instructions. That's like Microsoft Word, the instructions. That's the program itself. Then I have a cutting board, which is the CPU, and that is helped me to do what I'm doing right now, chopping apples. I'm dicing apples. So that's kind of how that memory piece works within the CPU. But yeah, 4 parts: decode, execute, fetch, store. Now we talked about memory. Let's look at this primary memory. Really, it's called RAM, random access memory. And I think we should probably all familiar with that. You've heard that a lot. This is volatile memory, meaning that it can only hold information while there's power applied to it. Now, most of the memory we use now is DRAM, which is called dynamic random access memory, meaning that that chip has to be refreshed every so often, while your computer's running, or it will lose data. Okay. So, 2 types of DRAM: SDRAM and DDR-DRAM. If you ever bought memory, and as a matter of fact, as you're doing your project, there's a couple of projects, in your research projects, and you're going to be doing research. You're going to go out there and look at different types of memory: DRAM, SDRAM, what DDR, SDRAM. What is all that? Pretty simple. I think pretty simple. Let's try to explain it. SDRAM, or synchronous dynamic random access memory, is synchronized with the computer clock. Inside of that your computer, right there on the motherboard, you have a clock. And if you ever seen if you ever looked at the specifications on your computer, it says this, it has a 3.2 gigahertz processor. That means that that's the speed that processor is capable of running. Okay, which is very, very fast. But there is a clock inside of your computer that times and synchronizes everything. It synchronizes the memory, it synchronizes the CPU, it synchronizes your bus, and that's just going how often it goes and looks at all the different I/O ports and bring information back and forth. All of that stuff is synchronized. So when we say SDRAM, that is dynamic random access memory that is synchronized with the clock on a clock pulse. That clock is clocking 1, 2, 2, 2. I don't know why I'm moving my head with my finger, but it just feels like the right thing to do. But it's pulsing up and down, right? So on every pulse, this SDRAM either brings something into memory or it takes something out of memory, all right? On every pulse. So I'm just going to use some simple numbers. Let's say that our clock was running, at 60 beats a minute. 60 beats a minute. So that means that I can bring something in or take something out, 60 times, because I can only do one thing on each beat, right? Not bad, okay? But then they said, hey, what if we can speed that up? And they did what they call double data rate SRAM. Now what this does, this is a type of SRAM that can send and receive data on a clock pulse. So now instead of having to wait for the next pulse to send and I'll receive, it can do both on one clock pulse. So now I can double my data rate from, let's say this example I use of 60, now I can have data moving at 120. I can do 120 actions with a 60 cycle per second clock, okay? So I've doubled that because now I can send and receive on one clock pulse. Now on the synchronous, I can send on a clock pulse, I can receive on a clock pulse. DDR, the way to go, it's much faster, much faster. Let's take a look at secondary storage. This is our hard drives, flash drives, SSDs, all of those things that is what we now call non-volatile memory. Non-volatile means that I can remove power from it and what I have stored in memory is still there. That's why you can shut your computer off and you still got all your information on your hard drive, or if you got USB thumb drives, you still get, you can carry those around with you with no power, or SSDs, which is, really taking the place now of a lot of your hard drives. So all of those things are called secondary storage. Nothing really crazy about that. I think we're probably going to go a little deeper in how this storage works in latter weeks. Next part of this computer system that we're going to talk about over the course of this class is operating systems. Let's talk about operating system architecture, because really this is the pulse, this is the heart of your system. Now at the very core of an operating system, and it doesn't matter what type of operating system, if it's Windows, if it's a Linux, if it's Mac, whatever it may be, at the core of that operating system is what we call a kernel. This is really where the secret sauce is in an operating system. All right, and what this kernel does, it manages the input and the output requests from your other software, and it manages things that are going to the CPU, things coming from the CPU, and things that are stored on secondary storage as well as your primary storage or your memory. So really, it is controlling everything. That's the heartbeat right there. Boom, 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 boom. That's the heartbeat of your operating system. Now, on the outside of that of the kernel, you have another layer, another ring. This is where your application or APIs, application program interfaces, and device drivers lie. So this is the small applets that allow the other rings to be able to talk or communicate with the kernel. And that ring is our operating system applications. Operating system applications are not the same as user applications. When we're talking about operating system applications, we're thinking things like file manager or your control panel. All of those things that you have on an operating system. Let's say if you load Windows 10 fresh, okay, all the like your control panel, your file manager, your file explorer, Windows Explorer, all of those are operating system application, and there are hundreds, and these are the applications that actually talk to the kernel. That these all of your operating system apps. Now, a way that we as humans are able to interface also with this is through a shell or command line interface, and this allows us to be able to. It's just a program that allows us to be able to talk directly through APIs and control activities on that kernel as well. It could be different types. If you're in Linux, you may use the Bash shell, and there are multiple shells. Windows, PowerShell, like I say, that's very popular now with Windows. But what it is, it's able, you're able to go into command line. And some of you probably seen this. It's like a little black screen with a where your cursor is, and you can type in, sys netstat or IF or IP config and talk directly to via program interfaces, application interfaces to the kernel. So when we look at an operating system, these are the three components that make up a basic operating system: the kernel, APIs or drivers, and your operating system applications. Now, on the outside of that, which is not a part of the of your operating system, this is where your user applications lie, your office products, video games, whatever you've installed. But I just want to be sure that we don't confuse user applications with operating system applications. Two different things. Okay, does that make sense? Here again, strategic pause, and let that marinate, let it soak in for a second. All right, pause over. Now let's bring all of these pieces together. Okay, we've talked about a lot of pieces, right? So now, from an architectural standpoint, or from a system design standpoint, we have to understand how all of these pieces work so that we can have an output or a product. So, if you remember, we started with hardware. And in this example, that's our CPU, that is our cache, memory. Like I said, a lot of the time this memory, even though I show it separate, this cache is actually on the motherboard itself. And some of the cache, depending on what level cache you're talking about, is actually on the chip of the CPU. Thing to remember about memory, the closer it is to the CPU, the faster it operates. The farther it is from the CPU, the more capacity you have. What do I mean by that? If you look at this hard drive that sits farther from your CPU, it's very slow, and relatively speaking, compared to your CPU that's operating at billions of operations per second. This is operating at the millions sometimes, or low billions of operations per second. But it can hold a lot. Now I look at this cache, which is very fast. It's basically able to operate pretty close to the same speed as the CPU. But now I'm talking about maybe the millions of the things. So it's fast, but it's small. You can't hold as much stuff there. So we got, like I said, we got our CPU. We have our memory. We got our main memory, our primary storage, secondary storage. Then on top of that, we overlay what we just learned about operating systems. Okay, so hardware. Here's the architecture of our operating system, along with user applications. Now we have to have some way to interface with this. And this is where our input-output devices, or IOs. And here again, that could be keyboards, mouse. How do you say mouse plural when you're talking about computers? Is it mouses? Mice? I don't know. I never understood that. But anyway, so you can have these types of devices. It could be printers, webcams, all these different devices, input, output. That allows us to communicate with hardware and with our via the operating system. Okay, so now let's talk about this. Look at it from a process perspective. Let's say if I want to do some type of process on my computer, what actually happens? Well, the first thing, after I have run a command that through some type of user application. Let's say Word. I want to open up a Word document, and I want to make some modifications to that Word document. Now, what do most of us do? We just click on that little icon that says Word, right? And it opens up. But lots of things happen in the process. So, even though I have my I/O here, it interfaces electrically, but it's also going to go up and run a command to open up Word. And what that does is that kernel, it says, okay, for me to do this, I have to have some type of code. I got to go find the code to do that. So that's where it's going to do a read from storage. The kernel is, because that kernel right here is what's controlling this storage device. When you format a hard drive, what are you really doing? Well, basically all you're really doing when you do format is that this kernel is setting up a structure on this hard drive that it understands, so that it knows where files are. It's basically setting up a file system on that hard drive. Many different types of file system. It's no different than if you open up a library. Let's say that somebody said, okay, we want you to open up a library, a brand new one. What is the first thing pretty much you're going to have to do? Well, is to come up with some type of file system. Okay, we're going to have a lot of books in here, so we got to figure out how we can file these so we know how to go get them the next time. Years ago when I was a little kid, we used to have the Dewey Decimal System, and that was the whole purpose of that. You look at those numbers with the little dot and everything. Yeah, it was the Dewey Decimal. But that was a filing system. No different than the kernel that talks to this drive has to set up a filing system, whether it's NTFS or NFS. I mean, there's a plethora I love that word plethora. We don't use it enough in our lexicon today. But there's a plethora of different types of file systems that can be set up here. But the kernel in this operating system is what does that, not the drive itself. So once that is set up, it knows, okay, I need to go to this file location and find this amount of code, code, and I'm going to do that's why I say it's going to do a read. It's going to read that, and it's going to write it into our primary storage or memory, our volatile memory. So it's going to take some code, bring it up here, write it into there. Also, it's going to push some of that is going to start working. Kind of think about that cutting board kitchen example into cache. Cache says, okay, I can do this. I know how to do this. The program is sitting here. What needs to be executed is sitting here. And it then does that fetch and store from cache to the CPU. So now that I got some code here, now the CPU is able to now start doing the executing, the decoding and executing of that code to open up that Word document, make whatever changes we want to make to that document. And then what does it do after it does the decode and execute? It lets the kernel know. The kernel then writes that. If I want to save it, I'm going to do Control-S or hit the little icon that looks like a save. And the kernel is then going to write that back to a file location, a predetermined file location on that drive. So that's how all of these pieces work together. From our I/O devices, from the hardware, the memory, whether it's volatile memory or primary storage, as well as non-volatile memory, secondary storage, operating system, kernel is kind of driving everything, but we're talking to that kernel via I/O devices that comes down through our operating system apps and our user system applications. Wow, a lot of things going on at the same time. A lot of moving pieces. But that is your basic architecture. If you kind of grasp that, it doesn't matter what system you go to. You can find these same types of components operating together in whatever computer system you're working on. All right, so now that we kind of understand that, how a single computing system, let's talk about the evolution of computing. This has been an interesting evolution. And you know what? I was just telling my lovely wife that I feel like I am probably one of the most fortunate individuals on the planet. Yes, for two reasons. One, I know Jesus Christ, and that always makes you very fortunate. And really the second is the generation I grew up in. When I joined the Air Force years ago, we won't go back to how far, I came in at the genesis of technology. I came in when we were still working on electromechanical devices. But along the way, I got to see technology evolve from electromechanical to tubes, to transistors, to integrated circuits, to where we are now with computers, networking, and all of these other things. So seeing that evolution, what it did for me was show, just like Solomon said, there's nothing new under the sun. Everything goes back to its beginning. All right, so if you think about computing, go back to the 60s, right? We started with mainframes. If you remember what a mainframe was, you probably see these on the old sci-fi. You walk in a room and it's just nothing but a huge room full of computing systems. And the way they would interface with that mainframe was with a dumb terminal, meaning that there wasn't any or very little processing power on that terminal. At the time, there were those green screens, those green phosphorus screens. But everything was sitting on the mainframe. So that's how you would interface with it. You had to have a connection to the mainframe, and you could do whatever you wanted to do. Well, that was pretty good. And it worked good for scientific reasons and for research and academia. Berkeley University, all these large universities at the time, they were working with mainframes. And then the government, the Department of Defense, they got interested in these things. Wow, what can we do with mainframes? We can start building, defense systems based on these large computers, and there were filled up rooms. Then along the way, a little later on in the 70s, someone, because with technological advances and the miniaturization of components, we were able to now, such as the transistor, start downsizing the size of these mainframes. They were still at the time huge, but really start bringing them down to where, you start having this thing called personal computers, PCs. What a concept. Now I can have a computer on my desk. What used to take up a whole room, now I can have it on my desk. And all of us, we got so excited. I know I went out and bought my first personal computer. It was a Radio Shack, Tandy, Trash 80, TRS 80. Oh, you could not tell me anything. I was cooking with gas, and it was great. I'd go home and I'd do stuff on that computer, but there was a problem. Whenever I wanted to share something with my other friends who had computers, who was as geeky as I was, I either had to save it to a tape drive or to a floppy disk and carry it over, and then that's how we shared information, and it was very clumsy at the time. Then in the 80s, that's when, smart people said, well, look, you know what? I'm a little too lazy to get up and carry this floppy drive. Why can't we just connect our computers together some kind of way? And that's where, we started going to this client server. Really, it started first peer-to-peer, right? Where I could just take my computer and hook it directly to another computer, and we could talk via one cable, between us. Two computers talking to each other. Now, that was pretty good, but it wasn't good enough because it still had its limitations. And that's when, companies like AT&T with their AT&T 3B2 system and other ones came up with this concept of a client and a server. Meaning that, hey, what if we had a big computer, but not as big as a mainframe, but a pretty big computer that held all of these programs and had storage. And now we can use different types of cable, and this was pre-Ethernet. We were still using coaxial cable to connect up several of these computers in a ring, and have these little T's on the back, and you hook up cable, and they all were connected together, and we could then share information, kind of in a work group, and have one computer that's a server that can control all these other ones. And that's how we got to the client server. And we're still in this client server environment now. If you look at most of the things we do, we're operating in the client server. We've gotten faster, technology's improved greatly along the way. Well, then about the 90s. Who can not forget the 90s, Who cannot forget Cyndi Lauper in the 90s? Girls just want to have fun. Was that the 90s? I think that was the 90s. But that's when web services, because now they say, well, wow, since we can hook these things up in a local fashion within our building or within one campus, why can't we connect to another campus? And that's when, like I say, a lot of your the Department of Defense, DARPA, some of these different agencies, as well as academia, like I say, Berkeley University, MIT, Lincoln Labs, and all these different schools also got involved in this. So now they started being able to connect up their computers, across the country. And what a concept. And from that, they want to be able to talk to each other, so they start standing up these bulletin boards. Okay? And that's how they would be able to post messages and things on a bulletin board. And it was an electronic bulletin board. And pretty soon it became worldwide. I could find anybody else's bulletin board. From that came, you guessed it, if you were following my etymology there, web services, worldwide electronic bulletin boards. That's where that came from, the term web. And right now you're going, I didn't know that. Yes, so that's what web services. So now that's, and that kind of segues me into understanding the difference between the web and the internet from an architectural perspective. Why? Because most of us throw these together, the web and the internet, when really it is two fundamentally different things. Okay, a web site or web service, that's just that. That's where your information resides. The internet, that's the superhighway to get you to those web services. Now, along the way with these web services, we have different web generations, and this is how the web evolved. Start with Web 1.0. And with Web 1.0, that was just a static, read-only, really monodirectional websites. That was kind of the very genesis of the .coms, meaning that you couldn't really do a lot with it. You could just go out and that's where the term surfing the web came from, because that's about all you could do. You go out and surf and look at stuff, but you couldn't really interact with it a lot. So that was Web 1.0. Later on, and this is, we're still here quite a bit in Web 2.0, the second generation of the web. This is what we call the participative web, or bidirectional. That's when we got the blogs, wikis, and all these things. So now we can go bidirectional. Not only can I go to a website and look at it, I can also request information, and that the owner of that site or whatever, they can send things back to me. We all do this all the time. Now it's bidirectional. Here, monodirectional. It was just one way. So we still work a lot with Web 2.0. But on top of Web 2.0, we're really moving into Web 3.0. Web 3.0 is what we call the semantic web. And if you think about semantics, and now we're talking about understanding how to communicate, how ontologies are put together across this web, and how it's readable, and now between machines and humans, because now we're able to understand how information is brought about. Now, what this has brought about with us also, and I'm sure we're all played with that, is because now human-machine interface. What does that really mean? Is that now when I go to Best Buy and I just look at a 65-inch television, and I don't do anything, I just go look at it. Then the next time I go out to the web, what do I see over here? If I'm in Facebook or wherever, I start seeing all of these advertisements on TVs. And you start thinking, how did it know that? Because that's what the semantic web is all about. It is looking at your activity and is coming up with the ontologies to know that this individual has been looking for televisions, because we see their search history and their patterns. So now let's start pushing that content to them based on their patterns. So that is why, thanks to Web 3.0, you start seeing all the advertisements and everything else of things that you've gone out and looked at, because it is using those types of ontologies. Now, where is it going? Well, Web 4.0. And Web 4.0 right now is still, now I won't even say in development, it is still in a conceptual state. And that is the symbiotic web. And now we're talking more of a blended environment, blended between human and machine interfaces. You're probably thinking, is this, iRobot? Well, not quite there yet, but no, it is where it's going to take the web to a much higher level of intelligence, using things like artificial intelligence and machine learning, where it will not only learn your patterns, but also start giving you the right responses. Here it's just learning patterns, and now actually give you the right responses or recommended responses and things like that, where it becomes more and more automated. So that is our web generations. And then what followed behind that is cloud computing. We all hear this term cloud. We're going to get into cloud deeper, but really all cloud did, believe it or not, kind of going back to the future, cloud almost brought us back to here. Because now what do we have? You have one single, I won't say single, but one ubiquitous location where we can get information. And what do we need to connect to it? It could be some type of almost a quasi-dumb terminal, just like we started here with the mainframes. Doesn't have to have a lot of services on it. As long as I have an internet connection, now I can get all my services from the cloud. Just like we started back here in the 60s, my dumb terminal didn't need services on it because he got all the services from the mainframe. So you see, we kind of took a big circle, back and forth. So that's kind of the evolution of computing. All right. Well, guys, we covered a lot of ground today, didn't we? Yes, we did. We talked about architecture, some of the basic computer designs, computer components, things like your OS, your operating system, hardware, memory, those types of things. We brought it all together. Let's look at how all these pieces fit together in a continuum. And then we talked about the evolution of computers. So yeah, when we talk about that, whether it's software, hardware, networking, the processes, procedures that associated with these different components, as well as the people, okay? All of these things are tied into the architecture or the system design. All right, guys, listen, hope you have a great week. Continue, if you have questions, please chime in on the discussions. And again, if you have questions, you've got my contact information right there. More than happy to chime in. All right, God bless. We'll see you next on the next video, probably. Yeah, we will. Take care.